We continue in section 1.2 of Rosen, Discrete Mathematics and its Applications, by talking about the concept of consistency. When we are giving many propositions, and in this case we'll be talking about specifications, which are a type of proposition, we want to know if it is possible to make them all true, to meet all of the specifications. And when we can, we say that the specifications are consistent. So here's the definition. A list of propositions is consistent if it is possible to assign truth values to the propositional variables inside of the proposition so that each proposition is true. Now here's an example. We have three propositions. We want to know if they're consistent. The first one is the diagnostic message is stored in the buffer or it is retransmitted. That'll be the disjunction of two atomic propositions. If the diagnostic message is stored in the buffer, then it is retransmitted. That will be an implication involving the same two atomic propositions. And finally, the diagnostic message is not stored in the buffer. So that'll be a negation of one of the atomic propositions. And we will label those atomic propositions P and Q as shown. When we do that, we can rewrite the specification symbolically as P or Q, P implies Q, and the negation of P. And now the question is, are there settings such that each of these three statements would be true? Are there settings for P and Q or values for P and Q? It turns out yes, because when P is false and Q is true, all three of these statements are true. So the specification is consistent. If it is also possible that there be more than one set of values for P and Q to make it true. It doesn't have to be just one for the system of specifications to be consistent, but there has to be at least one. All right, so what if we add a fourth specification? The diagnostic message is not retransmitted. Well, this is the negation of Q. And it turns out Q has to be true, but if we add this specification, Q has to be false. And so it turns out that when we add this specification, we create a set of inconsistent or non-consistent specifications. We'll show a truth table method for verifying this or analyzing this in the next video. First, I want to cover one more slide that we'll analyze also later with a truth table. This is a logic puzzle, a type of game, if you will, and you'll be able to use this technique to analyze whether you can get an answer or not. So here's the puzzle. An island has two kinds of inhabitants, knights who always tell the truth and knaves who always lie. All right, so in our example, we go to the island and meet two people, A and B. And A says B is a knight, and B says the two of us are opposite types. So the question is, can we tell what are the types of A and B? Well, first of all, there has to be consistent. There has to be some kind of answer. And then it turns out that if we want to be able to tell the types of A and B, there needs to be only one kind of answer. There can't be multiple, otherwise we wouldn't be able to tell. So what we're going to do is set this up as a consistency analysis and see if there's a single row that allows us to tell. All right, so the atomic propositions in this we'll say that A is a knight and B is a knight will be our atomic propositions P and Q. That means the negation of P would be A is a knave, and the negation of Q would be that B is a knave. Okay, well, let's think about A being a knight. If A is a knight, then P is true. And since knights tell the truth, Q must also be true because A says B is a knight. But B, being a knight, says that they're the opposite types. And that is false So that cannot be the solution. So A is not a knight, and therefore the negation of P must be true. Let's see if there's a solution there. Then if A is a knave, B must not be a knight because A would have been lying when A said B was a knight. And then, but B being a knave can say the two are of opposite types because B lies and they are not of opposite types. So there is the solution to this logic puzzle. And in the next video, we'll show a truth table technique for solving it and the system consistency problem from the previous slide.